The purpose of this lab was to observe a real-life and simulated model of a bar magnet falling through a conductive tube of aluminum foil. To do so, multiple key concepts would be used. The first concept is the Biot-Savart law, which calculates the magnetic field given a charge, a velocity, and a distance. The second concept is magnetic flux, which is the component of a magnetic field passing through a surface. The third concept is Faraday's law, which calculates an electromotive force based on the negative derivative of magnetic flux with respect to time. A fourth concept is Ohm's law, which relates current to voltage and resistance. And the final key concept used in this lab is Lorentz force, which can be determined using a current, a length, and a magnetic field. Through the use of all these concepts, I was able to analyze the behavior of a magnet falling through a conductive tube of aluminum foil. In the real model, the average time that my bar magnet stayed in the 46 centimeter long tube was 1.058 seconds. In the simulated model, the time the magnet stayed in the tube was 0.489 seconds. For the real-life model, I used a bar magnet, a 46 centimeter long tube wrapped with aluminum foil, and a video recorder. The tube had an inner radius of 1.5 centimeters and an outer radius of 2 centimeters. For each trial of the experiment, I held the bar magnet over the tube, started recording the video, released the magnet, and ended the footage once the magnet left the tube. I did this for 5 trials and analyzed the videos to calculate the average time that the magnet stayed in the tube. This time was 1.085 seconds. For the simulated model, I used Python to code a virtual model of the real-life system. First, I set the initial conditions and constants, some of which use measured properties of the real magnet and tube. Next, I coded a function that would return the magnetic field strength given a dipole and a distance. Then I coded a function that would calculate magnetic flux using a magnetic object and a ring object. Next, I coded a loop that would update the forces on the magnet and tube and would update the location of the magnet based on these forces. By running the program, a 3D model is displayed showing the magnet move down the tube. The time that the magnet stays in the tube for is 0.89 seconds. By observing the simulation, some details can be found. Near the magnet and the tube are red and blue colors shown to represent the magnitude of the induced current flowing through the ring. The blue color represents counterclockwise current and the red color represents clockwise current. Faraday's law can be used to determine this using the fact that the magnetic flux on the ring by the magnet points up and that the flux decreases for rings above the magnet and increases for rings below the magnet. If I were to flip the magnet around, the blue color would represent a clockwise current and the red color would represent a counterclockwise current since the magnetic flux would be flipped for both situations. The time spent in the tube in the real world is about twice as long as the time spent in the tube for the simulation. This could suggest that some error exists in the experiment, such as the magnet's dipole moment being incorrectly measured, or extra forces acting on the magnet in the real world, such as drag. By observing the velocity over time graph, it can be seen that the velocity decreases the entire time, implying that gravity is stronger than the magnetic force of the magnet. Seeing that the velocity nearly becomes constant before it leaves the tube implies that the magnetic force almost became equal to the force of gravity on the magnet. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Using Ohm's law, if the resistivity in the conductor was almost 0, the current would have to increase drastically. This change would greatly increase the magnetic force on the bar magnet. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? Cutting holes into the tube would affect the induced ring currents that allow for the magnetic force in the system. The magnetic force would decrease, and if holes are asymmetric, the magnet may rotate as it falls.